In the last video, we looked into how to set up the bridge or culvert across a one-dimensional plane. In this video, we are going to see how to modify and take care of the contraction and expansion around the bridges. So the idea here basically is that we have when we have a bridge opening and we have flow coming in, the flow tend to contract when they, especially from two cross sections, they begin to contract. And when they get to the opening, it begins to expand, as shown in the diagram. So we have some typical flow transition patterns. So it comes here, it contracts here, and begin to expand back. And this is how we model that in HECRAS for an ID flow transition pattern. So to do that in HECRAS, it's very important that we understand what is going on, and we take care of the cross sections that make this contribution. So it's also necessary to have the cross section very close to the bridge opening or culvert. So we're going to go into HECRAS and see how to modify that. So we click on the two cross sections. So we have this first upstream of the bridge opening. So we have this cross section. We're going to hit edit. So we'll see what's going on. So the contraction and the expansion we have here is for a normal channel when we don't have a bridge downstream or upstream. So what is this value? So we're going to hit this question mark and we'll see the value. So the contraction, no transition loss computed. We're going to use 0. This transition. For a gradual transitions along a normal channel, we have a contraction of 0, 0.3. When we have a typical bridge section or a culvert, we use this transition. When we see an abrupt change or transition along a cross section, we can say we have a dam, we have a wall or something, we can modify this abrupt quick transition using this contraction value. So basically, these contraction values have been derived by looking into some parameters, and it was derived through a combination of the expansion reach length, the contraction reach length, the expansion coefficient, and contraction coefficient. So these parameters were important through a series of studies to come up with the ideal contraction coefficient that has been generally adopted. So we're going to go back and we're going to do that two cross sections upstream. So we have to change these values 2.3 and 5 and 5. And we come down also, change this 2.3 and 5. Go to cross section downstream, change it to 0.3 and 5. And the next one, 3 and 5. So this is going to be a better representation of the channel. So we can 5, save geometry. We can go back and go to run steady flow to compute it. It's on. It is done. We can see that contraction. So this is how we go ahead and we can see if there are any problem. You can see that. So this is how we adjust for contraction and expansion, and also account for what is going on around. When we have a double culvert or bridge, we need to make sure we account for the contraction change or expansion change around the culvert. So now we can go ahead and save our work, and then in the next series we can continue to look into other aspects of this work, and I will see you in the next series.